I want you to take a second right now and just look around you.
Like really pause whatever you're doing and look at your immediate environment.
Exactly. Just look at the physical device you're using to listen to this audio right now. Or, the clothes you're wearing, the half-empty coffee cup sitting on your desk.
Right. And think about the digital world too, like the last app you opened on your phone.
Oh, yeah. Or that logistics network that like magically dropped a cardboard package onto your front porch yesterday afternoon.
Mhm.
Because every single thing you consume, every interface you interact with, every physical object that makes up modern human existence, it is all the output of a hidden, massive, incredibly complex machine.
It really is.
Yeah.
And well, that machine is called a process.
Right.
It's basically the invisible architecture of our entire world.
Yeah.
Because as consumers or even as workers, we are highly conditioned to only look at the shiny final product.
Like the car rolling off the lot.
Yeah. Yeah. Or the slick user interface of a new app.
Yeah.
But we are almost completely blind to the sequence of events, the thousands of interconnected steps and these microscopic delays that actually brought that product into existence.
And that invisible architecture is our entire mission for this deep dive today. We have gathered an absolute mountain of sources. I mean, research papers, engineering manuals, operational case studies, and we are going to uncover the universal physics of how work actually gets done.
Yes.
Because here's the part that I found so incredibly compelling when I was going through all this information. Whether you are managing like a massive multi-billion-dollar chemical refinery, or you are running the floor of an e-commerce fulfillment center, or even if you're just leading a remote team of software engineers building cloud infrastructure, there are undeniable, cold, hard mathematical laws that dictate your success or your failure.
Yeah, the overarching theme jumping out of every single source we looked at is the absolute domain neutrality of process engineering.
Domain neutrality.
Yeah. Because we have this tendency in modern business to think of physical manufacturing and digital software development as these two totally separate, completely incompatible universes.
Right, like the factory floor has nothing in common with Silicon Valley.
Exactly. But the underlying mechanics are literally identical. The exact same queuing mathematics that dictate the required volume of, say, a holding tank in a petroleum plant. Those are the very same mathematics that explain why a software engineer's code takes 4 days to get reviewed by their peers.
It is all the exact same math.
It is all the same math.
So we really need to unpack this carefully, like step by step, because I want to make a very specific promise to you, the listener, right now. By the time we finish walking through this material, you're going to walk away with a literal superpower.
Oh, absolutely.
You are going to have the ability to walk into any chaotic workplace, look at any broken system, or, join any frustratingly slow project, and you will immediately spot the invisible bottlenecks and the structural flaws that everyone else in the room is completely missing.
Yeah, you'll see the matrix.
Right. But to get to that level of insight, we have to strip away all the corporate jargon and start at the absolute foundation. We have to answer the most basic question, which is, what actually is a process?
So at its most fundamental, stripped-down level, a process is just a repeated transformation.
A repeated transformation.
Yeah. You are taking inputs, which could be raw materials or data or customer requests, and you are transforming them into outputs. And you are doing this through a sequence of interconnected activities over time.
Okay, that makes sense.
And crucially, you are doing all of this while consuming resources under strict constraints. So every single time that specific sequence happens, from start to finish, whether that is building one single car on an assembly line or reviewing one specific piece of code, that is called an instance of the process.
An instance. Okay, and to really analyze these instances, the literature insists that we have to look through two very different lenses simultaneously. The first one they talk about is the physical view. And this is essentially, well, it's the realm of hard science. It's grounded in the laws of conservation. Matter and energy cannot be created and they cannot be destroyed.
Basic high school physics.
Right. So if a certain mass enters a processing unit, it either has to leave that unit or it has to physically accumulate inside it. And this is the perspective that completely dominates traditional manufacturing, chemical engineering, and energy production. Because, you are dealing with the hard, unforgiving constraints of physical reality.
Exactly. I mean, if you feed exactly 1,000 pounds of raw steel into a factory, you are going to get exactly 1,000 pounds of something out the other side.
Right.
It might be finished car parts, it might be metal shavings and scrap, or it might just be a giant rusting pile of inventory sitting on the factory floor.
Yeah.
But the math has to balance. The physical view doesn't care about your quarterly goals, right?
Yeah.
It only cares about the conservation of mass. But then we have the second lens, which is the operational view. And this is where we shift our focus to look at the flow of discrete entities that are competing for scarce resources over time.
Discrete entities competing for scarce resources.
Yeah.
Okay, so we're talking about individual tasks queuing up for a specific machine, or like network requests queuing up to be processed by a specific server.
Yes,
And this is where the behavioral laws come into play, which seems to be the dominant framework for software engineering, global logistics, and, service industries.
it is. And the crucial insight here is that almost every real-world process requires you to use both lenses. You really can't just pick the one that feels most comfortable to your specific industry.
Let me test my understanding here with an everyday analogy. Tell me if I am tracking this correctly. Let's think about a really busy, popular restaurant on a Saturday night.
Okay, good example.
The physical view would be the kitchen manager in the back room. They are counting the pounds of raw beef coming in the delivery door. They are measuring the cubic feet of natural gas being burned by the stoves, and they are calculating the calories going out on the plates to the dining room.
Right.
The physical math has to perfectly balance, but the operational view, that is the angry, restless line of customers standing in the lobby waiting for a table.
Exactly.
Those people are discrete entities, and they are competing for a highly scarce resource, which is an empty table over a period of time. So my question for you, looking at all this operational research, is one of these views more important than the other? Or is it just catastrophic to ignore either one of them?
Oh, it is absolutely catastrophic to ignore either of them. Let's play out your restaurant scenario for a second.
Okay.
If your restaurant has a completely flawless math balance of beef and calories
Yeah.
your physical view is perfect, no waste at all. But your customers are waiting 2.5 hours for a table because your operational flow, the way you seat people and clear tables, is a complete disaster.
You're going to go out of business.
You're going out of business. Nobody will wait that long. Conversely, if your operational view is great and you seat everyone the second they walk in the door, but your kitchen is literally throwing half of its expensive prime rib in the garbage because of poor physical controls, you will go bankrupt even faster.
Right.
You just have to master the physical realities and the operational flow simultaneously.
Which naturally brings us to this incredible translation dictionary that pops up in the sources. I found this so helpful because, professionals get so incredibly tribal about their own industry's jargon.
Oh, constantly.
They think their problems are totally unique. So let's do some translating across these domains. In a traditional manufacturing environment, you have a machine. What is the mathematical equivalent of that in the software world?
So in software, that capacity-bearing machine is a server or like a continuous integration build runner or even just a human being doing a code review.
Yeah.
They all function as machines in the math.
Okay. And in manufacturing, they talk all the time about a WIP, buffer work in process, just sitting in bins on the floor waiting for the next step. What is a WIP buffer in an IT department?
It's a message queue in an architecture like Kafka. Or it's a backlog of open, unresolved support tickets sitting in a system like Jira or Zendesk.
And what about cycle time on a physical assembly line, like the actual time it takes to build the widget?
That translates directly to a build duration for a software compile or a service time for database resolving a web request. And, we really need to pause and be incredibly clear about this for the listener. This is not a metaphor.
Right.
We aren't just using colorful, poetic language to compare two different things. The exact same queuing theory equations govern the physical factory floor and the abstract cloud server.
That is a really profound realization, but it also raises a massive practical problem. If this math governs everything universally, how on earth do we actually isolate a process to study it?
Yeah, it gets complicated fast.
Because reality is infinitely, overwhelmingly complex. If I want to map out the process of, say, a local coffee shop, where do I stop? Do I have to mathematically model the farmer growing the coffee beans in Colombia?
Right.
Do I have to model the global shipping lanes? Do I include the local weather patterns affecting how many people want hot coffee today? We have to figure out how to, draw a box around the problem.
And that is exactly the concept of system boundaries and topologies.
Mm.
If we want to study a process without losing our minds to infinite variables, we have to formally define it as a system. The literature gives us a very specific, rigorous anatomy for this, referred to mathematically as A tuple.
A tuple.
Yes, it consists of 5 distinct components.
Okay, before you list them, bring them down for us, because tuple sounds like something from an advanced computer science class, and I want to make sure we don't lose the thread here.
Fair enough. A tuple is really just a mathematical way of saying a finite ordered list of elements. For our purposes, defining a system requires 5 things. First, you have the components themselves. These are the capacity-bearing elements that actually do the work. The espresso machine, the barista, the blender.
The physical or digital things doing the task.
Exactly. Second, you have the relationships. These are the directed connections that show how things physically or logically move from one component to another.
Oh.
You can't just have a barista and an espresso machine. You have to define the relationship of how the coffee moves between them.
Got it. Components do the work. Relationships are the pathways. What are the other 3?
Third and fourth are the inputs and the outputs. What is coming in from outside our defined box and what is leaving it.
Simple enough.
And the fifth is the transformation function. This is the actual logic of how the internal state of the system changes when an input moves through the components and becomes an output.
Okay, so that gives us the anatomy. But the literature makes this huge flashing red light warning about this next part. The most dangerous, consequential decision a manager or an engineer can make is deciding exactly where to draw the boundary of that system.
Oh, absolutely.
They talk about open versus closed systems. Now, I assume almost all real-world business systems are open systems, right? Meaning things cross the boundary from the outside world into our box.
Yes, outside of theoretical physics, you are always dealing with open systems. And the choice of where you draw that boundary completely alters your perception of reality.
How so?
Let me give you an example. Let's say you are a manager trying to speed up a single sluggish workstation in a factory. If you draw your system boundary incredibly tight, just a box around that one specific worker and their one specific machine, then the supplies arriving from the previous station upstream are just treated as a mathematical variable, an arrival rate.
Right.
You just blindly assume they will show up when they are supposed to.
Because they are outside the box. You aren't managing them.
Exactly. But if you draw the boundary wider and you put the box around the entire factory floor, now that upstream supplier isn't just a number. They are a component inside your system.
Oh, I see.
And that means their actual messy behavior, their machine breakdowns, their shift changes, their delays, all of that has to be explicitly modeled and accounted for.
Oh, man. This perfectly explains a classic management failure that I've seen in so many different companies. It drives me completely crazy.
That's it.
Well, a manager will meticulously optimize everything inside the arbitrary boundary they chose for their department. They force their team to work 10% faster. They optimize every spreadsheet. They cut out every wasted second of their internal workflow, and they give themselves a huge pat on the back.
Oh, yeah.
But the actual problem, the reason the overall project is 3 weeks late for the customer, is sitting just a few inches outside of their departmental boundary. They're waiting on a vendor, or they're bottlenecked by a legal approval from a different team. They optimized the wrong box.
It's a tragedy of local optimization. And it happens constantly because human beings have a deep psychological need to draw boundaries around what they can directly control.
That makes total sense.
Right. A department head controls their department, so they draw the boundary there and optimize it. They rarely draw boundaries around the actual end-to-end flow of value because that crosses departmental lines and gets politically messy.
Oh, politics ruins everything.
It does.
Okay.
But if you optimize a subsystem without understanding its relationship to the whole open system, you don't actually speed anything up. You usually just create a much bigger, more expensive traffic jam slightly further down the line.
Okay, so let's say we avoid that trap. We've drawn our boundary correctly around the true flow of value. We know exactly what's inside our box. Now we need a map of the territory. And in process engineering, that means creating process flow diagrams, or PFDs. And the sources are very adamant about this. A PFD is not just a casual doodle you sketch on a whiteboard during a Tuesday morning brainstorming session.
Not at all. In this discipline, a PFD is a rigorous data structure. It is a mathematical directed graph. The nodes in the graph represent the components, the workstations or servers, and the edges, or the lines connecting them, represent the streams of entities flowing between them. And before you are allowed to do any mathematical analysis, you have to run 3 vital structural checks on your PFD to ensure it actually represents reality.
Walk us through those 3 checks.
First is connectivity. Are there any orphaned units? If you have a machine or a team on your diagram that isn't connected to a downstream output, your model is fundamentally broken.
Yeah.
Or, you have literally built dead capacity into your system that serves no purpose.
Right. That's just a waste of space.
Exactly. Second, you have to look for merges and branches.
Merges being where two lines come together.
Right. Think of an assembly line where the chassis of a car meets the engine. That merge point is incredibly important because that is where entities contend for resources. If the engines arrive faster than the chassis, a queue starts to form. Merges are where traffic jams are born.
And the third check, which I know is going to be a huge part of our discussion today, is cycles. The dreaded rework loops,
Oh.
where a product goes down the line, fails a check, and gets sent backward. We are going to dive really deep into why rework is where productivity goes to die. But before we calculate the cost of that rework, we have to establish the granddaddy of all process laws. The foundational rule that makes all of this math work, the conservation of entities.
It is the ultimate audit equation. It is brutally, beautifully simple, and it is entirely impossible to cheat.
I have the equation right here in my notes. It states arrivals equal departures plus the change in work in process, or WIP.
It is the operational equivalent of the conservation of mass. If a discrete entity, like a customer, a part, a data packet, enters the system boundary, it must either eventually leave the system boundary or it must still be inside it.
There is no third option.
There is no third option. It cannot vanish into thin air.
Okay, I want to apply this to a specific scenario from the research because it is so painfully real. I think anyone who has ever worked in a corporate office will recognize this.
Let's hear.
Two directors at a mid-sized tech company are in a heated argument over an operations dashboard. The company's ticketing system logs the data for the quarter. It shows that 5,200 new customer support tickets arrived over the last 3 months. It also logs that the team successfully closed 4,900 tickets.
Okay.
But the fancy executive dashboard up on the monitor shows that the number of open pending tickets, which is our work in process, our WRP, is completely flat. The line graph hasn't gone up or down. Why is this dashboard lying to these directors?
Well, it fundamentally has to be lying. The math is non-negotiable. If 5,200 tickets arrived and only 4,900 departed, there is a physical difference of 300 tickets.
Right. 5,200 minus 4,900.
Exactly. Those tickets didn't evaporate. So the change in WIP must be positive 300. The queue grew by 300. If the dashboard says the open ticket count is flat, you don't have a minor reporting glitch. You have a severe data integrity problem that is hiding a failing process.
How does that happen in real life? The software didn't just delete them, right?
Usually it's a mix of bad system design and office politics.
Oh.
Maybe the ticketing system is dropping events due to a bug. Or, more likely, maybe an employee's double counting closures to hit a quota. Or, even more insidiously, maybe tickets that get too old are being automatically transferred into a secret pending administrative review status that the main dashboard has been programmed to ignore so the metrics look better for the VP.
Wow, just sweeping it under the rug.
Happens all the time. But the conservation law doesn't care about office politics. It exposes the lie immediately. If arrivals and departures don't match the change in WLBP, your data is garbage.
It's the ultimate lie detector. You can't argue with the audit equation. Okay, let's talk about the silent killer we mentioned earlier when we were looking at the diagrams. Cycles. The rework trap.
Yes, let's.
I really want to walk through the math on this continuous delivery pipeline example from the sources. When I first read this, I actually had to stop and write it out on a notepad because it is so counterintuitive. I want to play the role of the confused manager here, and I want you to walk me through why my team is failing.
Let's do it. Lay out the parameters of your pipeline.
Okay, so I manage a software development team. Our raw input is new code commits. 40 new commits arrive per day from my developers. They go to an automated build stage. Our data shows 92% of them pass this stage. The 8% that fail just get kicked out of the system entirely. They bounce back to the author.
Right.
Then the survivors move to an automated test stage, and 95% of those pass. Finally, they hit a manual human review stage. And here is where things get messy. The senior reviewers improve 80% of the code, but they find flaws in 20% of it, and they send that 20% all the way back to the very beginning, back to the automated build stage for rework.
Which creates a classic structural cycle in your process flow diagram.
Right. So as the manager, I am looking at my staffing. I say, okay, our arrival right at the front door, the build stage is 40 commits per day. I will provision my servers and staff my team to handle exactly 40 builds a day. And yet, my team is constantly underwater, the servers are crashing, and everything is delayed. What am I missing?
You are missing the compound interest effect of rework. Your assumption is entirely wrong, and this is exactly why queues mysteriously back up in companies all over the world. The effective arrival rate at that first build stage is not just the 40 new commits. It is those 40 new commits plus the reworked commits that are constantly looping back from the review stage.
Okay, so help me calculate the real number. How do we figure out the actual load on that first stage? Let's do the algebra slowly so I can wrap my head around it.
We need to work backwards from the review stage. Let's create a variable for the rate of commits that actually reach that final human review stage. Let's call it R.
Okay, R.
To get to R, a commit first has to survive the build stage, which you said has a 92% pass rate, and then it has to survive the test stage, which has a 95% pass rate.
Okay, so R is going to equal 0.92 multiplied by 0.95 multiplied by whatever our total effective arrival rate is at the front door.
Correct. If you multiply 0.92 and 0.95, you get 0.874. So R equals 0.874 times the effective arrival rate. In plain English, that means 87.4% of every single thing that goes into the front door of the build stage eventually survives long enough to make it to the human review stage.
Got it. Now, at that review stage, 20% of R gets rejected and sent back to the front door as rework. So our total effective arrival rate at the front door isn't just 40, it is our original 40 new commits plus 20% of R.
Right. And since we just established that R is 0.874 times the effective arrival rate, we multiply 0.874 by that 20% rework rate, which is 0.20. That gives us 0.1748.
Let me make sure I'm following. So if I write this out,
Sure.
the equation is effective arrival rate equals 40 plus 0.1748 times the effective arrival rate.
Yes.
If I want to solve for the effective arrival rate, I need to group the terms. I take 40 and I divide it by 1 minus 0.1748. So 40 divided by 0.8252, let me run that. That equals 48.47. So basically 48.5.
Exactly. 48.5 builds per day.
I mean, just look at that gap. As the manager, I built a system designed to handle 40 builds a day. But because of a 20% rework loop hidden at the very end of the process, that very first stage is actually getting slammed with 48.5 builds a day.
Yep.
That is a 21% increase in workload that I didn't even budget for.
And this is why we call it a silent capacity killer. Your customers didn't ask for that 21% extra work. The market didn't demand it. Your product didn't get 21% better. The process is literally consuming its own capacity just to stay afloat.
Wow.
And if your build servers or your engineers are only staffed to handle 40 builds a day, you are going to fall behind instantly. And the tragic part is the management team won't understand why, because the executive dashboard says, great news, we only received 40 new customer requests today. We should be fine.
It is incredibly frustrating to realize how much human effort is wasted just spinning in these invisible structural loops. And this realization perfectly transitions us into the next major concept in the material, which is the physics of time.
A very important transition.
Because a flow diagram, no matter how accurate, is just a snapshot of a single moment. But processes exist and unfold in time. So what happens when the flow doesn't perfectly balance over days, weeks, or months? The sources split this reality into two distinct regimes: steady state and dynamics. Let's start with steady state.
So steady state is the ideal condition. It is the holy grail of process engineering. It occurs when your state variables, like your queue length or your throughput, remain constant over time.
Okay.
The math here is purely algebraic. You see this in a chemical plant that is running perfectly at its engineered set points, or in a highly optimized warehouse right in the middle of the shift where the rhythm of the workers is perfectly matched to the volume of incoming orders. The inflow exactly equals the outflow.
But then you have the dynamic models, and this is when time becomes an aggressive factor and you have to start using differential equations. This is the regime of startup scaling rapidly, or unexpected demand surges, or massive system failures.
Exactly. When things are actively changing, you are operating in the dynamic regime. And the single most critical dynamic concept for any manager or leader to deeply understand is what mathematically happens when capacity falls short of demand.
Yes, the infinite backlog. Listeners, I really want you to picture this scenario because it plays out in thousands of companies every single day. Let's say you manage a customer support desk. Every single day, like clockwork, 120 new support tickets arrive from angry customers.
Okay.
But your team, working as hard and as fast as humanly possible without taking breaks, can only resolve and close 96 tickets a day. Walk us through the brutal reality of this math.
It is brutal because it is perfectly linear and it is entirely relentless. If 120 tickets arrive and only 96 close, your backlog, your queue, grows by exactly 24 tickets every single day.
Right.
On day 10, you have 240 unresolved tickets. On day 100, you have 2,400 tickets. There's absolutely no steady state here. The differential equation shows the backlog growing linearly toward infinity.
It never stops.
It will never, ever stabilize. It'll just keep growing until the system collapses, unless one of two things happens. You either permanently increase your capacity to close more than 120, or you permanently decrease your arrivals by stopping customers from submitting tickets.
But this brings up a massive psychological question that the math doesn't answer, but human behavior does. Why is it so incredibly hard for human beings, particularly smart, highly paid executives, to accept this reality?
That is the million-dollar question.
I have personally seen managers stare at dashboards for months, watching the backlog grow by hundreds of tickets a week, and instead of fixing the math, they just schedule more alignment meetings, or they bring in a motivational speaker, or they send out an email telling the team they need to work smarter, not harder. Why do we hope the system will magically fix itself when the math clearly shows a line going to literal infinity?
It is a profound cognitive blind spot rooted in how we experience the world. As humans, we are deeply wired to believe in reversion to the mean. When we experience bad weather, we know sunny weather is coming. So when a manager sees a spike in the backlog, their brain says, oh, it's just a busy week, it's an anomaly, it will quiet down next week. But they are confusing average arrival rates with peak arrival rates. If your average arrival rate exceeds your maximum capacity, there is no quiet down. There's no sunny weather coming.
It's just a constant hurricane.
Exactly. Managers resist this mathematical truth because accepting it means they have to make politically and financially painful choices. They either have to hire more people, which blows up their department budget, or they have to turn away customers and degrade the service level, which hurts revenue.
So they just ignore it.
They subconsciously choose a third option, delusion. They let the queue grow indefinitely, hoping for a miracle, which inevitably destroys team morale, burns out their best workers, and ultimately ruins the customer experience anyway.
Delusion by dashboard. It is a terrifying phenomenon. Okay, so if delusion is the disease, how do we cure it? We have to measure the flow accurately so we can't hide from the math. Which brings us to the core metrics of process engineering and the absolute magic of a concept called Little's Law.
If you take absolutely nothing else away from this entire deep dive, you need to learn and internalize what we call the core 4 metrics. These 4 numbers tell you the health of any system.
All right, lay them out.
First is throughput. This is the rate at which completed, finalized entities successfully exit the system per unit of time. Jobs per hour, cars per day.
Second is cycle time. This is the total elapsed time that one specific entity spends inside the entire system, from the exact moment of entry to the exact moment of exit. And this includes all the time it spends just sitting around in a queue waiting for someone to look at it.
Yes, waiting is a huge part of it.
And the sources make a really vital point here. You cannot just look at the average cycle time. You have to look at the tail of the distribution, the 85th or 95th percentile. Why is that tail so much more important than the average?
Because averages lie to your customers. Let's say you run an e-commerce shipping company. If your average delivery time is 2 days, you might think you're doing a great job. But if your system has high variance and 10% of your packages take 14 days to arrive, those 10% are going to be your loudest, most furious customers.
They are the ones leaving the 1-star reviews.
Exactly. They are calling the support desk, yelling at your reps. The tail of the distribution is where all the actual pain, cost, and reputational damage lives.
Okay, the third metric is work in process, or WIP. We've talked about this a bit. It's the total number of entities currently residing inside the system boundary at any given moment.
Right.
And the fourth metric is utilization. The fraction of available time that a resource, a machine, or a person spends actually doing productive work versus sitting idle. But here is where management theory gets it entirely backwards, and it causes so much dysfunction. We need to talk about the entity clock versus the resource clock.
This is a profound distinction, and misunderstanding it is the root cause of most inefficient workplaces. You have 2 very different perspectives. The entity, let's say the entity is a customer's mortgage application experiences cycle time. The entity's clock is ticking from the moment it is submitted until it is approved. It cares about speed.
Right.
And importantly, most of that time, that application isn't being worked on. It is just sitting in a pile on a desk waiting. Now, flip the perspective. The resource, which is the human loan officer, experiences utilization. Their clock measures how busy they are during their 8-hour shift.
So the classic managerial error is that the manager optimizes for the resources clock instead of the entity's clock. A manager looks at a loan officer and says, I am paying you for 8 hours of work. I want you busy 100% of the time. So to guarantee the worker is never idle, the manager piles up a massive stack of 50 mortgage applications on their desk. The resource utilization looks fantastic. The worker is sweating, clicking, typing all day long. But the entity cycle time is a complete disaster because every single application in that stack is going to wait weeks to finally get processed.
Precisely. You have artificially created a massive WIP buffer just to ensure your worker never has a free minute. And the relationship between these specific metrics, WIP, cycle time, and throughput, is governed by what is arguably the most famous and important equation in all of operational physics, Little's Law.
WIP equals throughput multiplied by cycle time.
It is stunningly elegant. And its true power, what makes it so revolutionary, is what it doesn't assume. Little's Law assumes absolutely nothing about your arrival patterns. It doesn't care if customers arrive evenly spaced or all at once in a massive surge.
Oh.
It assumes nothing about how you prioritize the queue, whether it's first in, first out, or triage based on severity. It applies equally to a single coffee machine or a sprawling, complex global supply chain. If the system is stable and you know two of those variables, you absolutely mathematically know the third.
Let's look at a practical application of this, because the first time you see it, it honestly feels like a magic trick.
It really does.
Let's go back to our IT support desk. Let's say they've hired more people and stabilized the system. They consistently close 48 tickets a day. That is our throughput. And if we look at the software dashboard at any given random moment, there are an average of 36 open tickets sitting in the queue. That is our WIP. Little's Law says we can figure out the exact average cycle time, how long a customer waits, without needing to pull a single timestamp from the database, right?
We can do it in our heads. WIP equals throughput times cycle time. So 36 equals 48 times cycle time. You divide 36 by 48 and you get 0.75.
Wow.
Your mean cycle time is exactly 0.75 days. You didn't need to track a single specific ticket from start to finish. You didn't need a complex software tracking tool. The sheer physical geometry of the system dictates the time.
Okay, let's reverse engineer this equation, because this connects perfectly to things like Kanban boards and agile workflows that everyone in the tech and corporate world is so obsessed with right now.
Oh, absolutely.
Let's say I'm running that support team, and my goal, my hard promise to my customers, is a 4-hour cycle time, which is half of an 8-hour workday, so 0.5 days. And I know my team's maximum throughput is 48 tickets a day. What does Little's Law tell me I mathematically must do to hit that 4-hour promise?
It tells you exactly what your WIP limit has to be. You have to solve for WIP. If throughput is 48 and your target cycle time is 0.5 days, you multiply 48 by 0.5.
Which is 24.
The answer is 24. You are mathematically forbidden from having more than 24 tickets open in your system at any one time. If you allow 25 tickets to accumulate, the physics of the system guarantee that your average cycle time will exceed 4 hours. It is inescapable.
So, capping WIP, putting a hard limit on your Kanban board, and refusing to start new work until old work is finished isn't just a trendy, agile philosophy or a nice way to reduce employee stress.
No, not at all.
It is a mathematical prerequisite for speed. If you want a fast cycle time, the system has to remain relatively empty.
Yes. Being empty, having low WIP, is the mathematical prerequisite to being fast.
Which flies in the face of everything capitalism and traditional management teaches us about efficiency. And that brings us to the most counterintuitive part of this whole deep dive, the utilization trap. Because if we are measuring our resources, our workers, our servers, the deep-seated instinct is to want them working at 100% utilization. I'm thinking for an 8-hour shift, I want 8 hours of relentless output. But here is where the math literally slaps us in the face.
If the world were a perfectly ticking clock, if customer arrivals came exactly on a metronome, 1 every 5 minutes, and every single task took the exact same number of seconds to complete with 0 deviation, then 100% utilization would be totally fine. You could run the system perfectly hot.
But reality doesn't work like that.
No, reality contains variability. Variability is the enemy of utilization.
Because humans get sick. A specific line of code takes 3 hours to debug instead of 10 minutes. A customer calls in with a bizarre, complicated question that isn't in the script.
Exactly. Variability changes the physics of the queue entirely. And to understand why, we have to look at the MM1Q and Kingman's formula.
Now, I know the sources get deep into the Greek letters here, but we need to break down the actual mechanics of this formula conceptually. Kingman proved that waiting time in a queue is the product of 3 independent things.
Waiting time equals the degree of variability, multiplied by the utilization factor, multiplied by the actual duration of the task.
Let's focus on that utilization factor, because this is where the nonlinear explosion happens that catches every manager completely off guard. As your utilization approaches 100%, what actually happens to the wait time?
It doesn't just increase slightly, it goes asymptotic. It explodes toward infinity. Let me explain the mechanics of why this happens.
Please do.
If a worker is at 50% utilization, they are idle half the time. If a really difficult task comes along and takes twice as long as normal, it's fine. The worker just eats into their idle time to catch up, and the next task in line isn't delayed at all. Even if you push them to 80% utilization, the wait times might double, but the worker still has 20% of their day to recover from hiccups.
Okay, that makes sense.
But what happens when you push a worker to 95% or 99% utilization? They have zero recovery time. If one single task takes 5 extra minutes, every single task behind it in the queue is permanently delayed by 5 minutes because the worker never has a free moment to catch up.
Oh, wow.
The delay just cascades and compounds. The last few percentage points of utilization are purchased with unbounded, almost infinite delay for the entities waiting in line.
It's exactly like a highway. Think about a massive interstate highway at 3.00 a.m. It's at 10% utilization capacity. You fly down the road at 75 miles an hour, changing lanes freely. At 2.00 p.m., it's at 60% capacity. There are more cars, you might have to tap the brakes occasionally, but you're still doing 65 miles an hour. But at 5:00 p.m., when rush hour hits and the highway hits 98% or 100% capacity, it doesn't just slow down by a few miles an hour. The entire system collapses. It becomes a parking lot. Speed drops to literally zero. 100% utilization is a traffic jam.
That is the perfect analogy. The physical space on the highway is the capacity, and the cars are the entities. When utilization hits 100%, flow stops. And yet managers constantly try to run their teams like a highway at 100% capacity, stuffing their calendars with back-to-back meetings, and then they yell at the team when projects stall. Let's look at the Slack mandate example from the material to see how variability makes this even worse.
Yes, this blew my mind. Let's say you have a code review stage. The actual work of reviewing the code takes exactly 10 minutes. The human reviewer is kept at a steady 80% utilization. With normal, everyday variability, a new piece of code waits in the queue for about 40 minutes before that 10 minutes of actual work even begins.
Which already hurts your cycle time. But then let's say the variability gets bursty.
Bursty, meaning it doesn't come in evenly. Like, it's Friday afternoon, everyone wants to go home, so every engineer on the team submits their code for review at the exact same time at 3:00 p.m.
Yep, very common.
The total utilization for the week is still exactly 80%. The work still takes exactly 10 minutes to do. But because of that bursty arrival variability, the math dictates that the average wait time jumps from 40 minutes to over 100 minutes. It takes 2.5 times longer to get anything done, even though nobody is working any slower.
Exactly. Waiting equals variability multiplied by utilization. If variability spikes, waiting spikes. So what is the inescapable conclusion here? If you have a system with high variability, which literally all human knowledge work does, you cannot run your resources at high utilization.
You just can't.
Having slack capacity, meaning having workers occasionally sitting around seemingly idle, is not laziness. On a critical path, slack is a mathematical requirement for flow. If you remove the slack to save money, you destroy the flow and you destroy your cycle time.
Slack is a mathematical requirement for flow. That is a paradigm-shifting realization. Someone needs to embroider that on a pillow and put it in the office of every MBA student on Earth.
I'd buy one.
But this begs a very practical question. If I am the boss and the math says I can't run everything at 100%, where do I focus my resources? If things are broken, how do I know what to fix first? Because I can't optimize everything.
This is the discipline of hunting the bottleneck. In any process, the bottleneck is formally defined as the specific stage with the minimum effective capacity. And remember from our rework discussion, that is net of yields, downtime, and rework loops.
Okay.
It is the absolute unyielding speed limit of your entire system. If step A can do 100 units an hour, step B can do 50, and step C can do 100. Your system throughput is 50. Step B is the bottleneck.
And this leads us to the theory of constraints, which was popularized by Eliyahu Goldratt. The sources break this down into 3 golden rules. Rule number 1, an hour lost at the bottleneck is an hour lost to the entire process.
Because if the bottleneck stops working for an hour, the final output of the entire factory drops. You can never, ever recover that lost time because the bottleneck is already running at maximum capacity.
Right.
It has no slack to catch up.
Rule number 2, an hour saved anywhere else is an illusion.
This is the rule that management teams struggle with the most. If you spend $1 million to speed up a machine that is not the bottleneck, you do not get a single extra drop of finished product out the door.
Okay.
You just create more inventory piling up in front of the actual bottleneck faster.
Right.
You haven't improved throughput. You've just created structural idle time for the non-bottleneck machines. It is a complete waste of money and effort.
And rule number 3, Bottlenecks move. If you successfully fix the bottleneck, congratulations, you just promoted a different stage to be the new bottleneck. Let's explore the danger of misunderstanding these rules with a scenario from the sources. The idle packers scenario. I'm going to play the role of the ruthless efficiency manager again.
Go for it.
I walk into my e-commerce fulfillment center on a Tuesday. I see that the workers packing the boxes at the end of the line are standing around idle 40% of the time, just talking to each other. I'm furious. I am paying them to work. So I announce that I am firing a third of the packers right now to save on payroll costs. That's just good, lean business, right? But the data shows that the picking stage, the workers running around grabbing items off the shelves, is actually the bottleneck. Why is my plan to fire the packers a total disaster?
Because you are confusing structural idleness with excess capacity. Right now, your packers are much faster than your pickers. That 40% idle time you see isn't laziness, it is structural slack dictated by the bottleneck. If you fire a third of the packers, their effective capacity drops drastically. Suddenly, they might become slower than the pickers.
So by trying to optimize a non-bottleneck, I just move the bottleneck?
Exactly. You intentionally move the bottleneck to the very end of the line. And worse, you destroy the system's resilience. What happens when demand surges by 15% next month for a holiday sale?
I'm guessing bad things.
Very bad things. Your pickers, who were the old bottleneck, could maybe handle it by working a little overtime. But your newly decimated packing team, which has zero slack, will instantly be overwhelmed. Boxes will pile up on the floor, cycle times will explode from hours to days, and you will fail to ship orders to your customers. You tried to save a few bucks on payroll by optimizing a non-bottleneck, and you destroyed your company's ability to generate revenue.
And we have to note something crucial here about modern work. In knowledge, work, tech, finance, law, marketing, the bottleneck is almost never the compute power or the software. The bottleneck is almost always human.
Oh, without a doubt.
It's the approval stage. It's the legal review. It's the middle manager who insists on personally signing off on every single document, but who is trapped in Zoom meetings 8 hours a day.
Humans are the ultimate high variability, high utilization constraints. We are slow, we get distracted, we have bursty arrival times, and we constantly become the choke point in digital workflows.
So true. Okay, let's pivot to talk about efficiency in a broader sense. We've talked extensively about speed, flow, and finding bottlenecks, but what about the quality of the work and the cost of running the process? The sources give us an incredibly precise metric for this called OEE, Overall Equipment Effectiveness.
OEE is a brilliant framework because it refuses to just give a machine or a process a generic grade. Instead, it decomposes effectiveness into three multiplicative losses. It's availability, multiplied by performance, multiplied by quality.
Let's define those really quickly. Availability is the fraction of time the machine is actually turned on and running when it is scheduled to be running. It measures downtime.
Right.
Performance is how fast the machine runs while it's on compared to its theoretical maximum speed limit. And quality is the percentage of good, usable units it produces versus defective units that have to be thrown away or reworked. Why is multiplying these three distinct factors together better than just giving a machine a general health score?
Because an aggregate score allows machines and managers to hide their sins. If a machine has an overall OEE of 84%, that tells you it's losing 16% of its total potential value. But where is it losing it? You have no idea how to fix it.
Yeah, 84% could mean a lot of things.
Exactly. But if you decompose the metric, you might see that availability is 90%, performance is 95%, but quality is a disastrous 98%. No, wait. If it's bad, quality would be, say, 70%. The decomposition names the exact loss you need to attack. It tells you immediately whether you need to dispatch the maintenance team to fix downtime, the engineering team to speed up the motor, or the quality control team to figure out why the machine is chewing up the raw materials.
It's precision diagnostics. It stops you from guessing. But let's look at efficiency from the other perspective, from the perspective of the entity, the thing actually moving through the system. This is called flow efficiency. This is calculated as the amount of time value is actually being added to the entity, divided by the total cycle time it spends in the system.
And this is where the numbers get incredibly depressing for anyone in modern business.
Depressing is an understatement. The sources state that in standard corporate knowledge work, flow efficiency is frequently around 7.5%.
Yeah, it's rough.
Let that sink in. That means for every 100 hours a project takes to get completed from start to finish, actual valuable human work is only being done on it for 7.5 hours. The other 92.5 hours, the project is just sitting in a digital queue, waiting in an inbox for someone to look at it, or waiting for a weekly alignment meeting.
Which brings us right back to Kingman's formula and the utilization trap we discussed earlier. Why is it waiting for 92 hours? It's waiting because the human resources, the reviewers, the approvers, the specialists, are being run at 99% utilization.
Wow.
Lean practice, at its core philosophy, is a relentless war on this waiting time. It's about structuring the flow, capping the WIP, and creating slack so that when a piece of work actually starts, it moves continuously through the system without stopping until it is done.
And what I found truly fascinating in the sources is how this exact same math ties directly into environmental sustainability. There is an entire section introducing the carbon footprint as a hard process metric. For a long time, corporate sustainability has felt like this, fuzzy, PR-driven ethical initiative. It's a slide in an annual report to make investors feel good. But the sources argue that sustainability is just pure process math.
It is exactly the same mass and energy balance math we discussed in the physical view at the very beginning of this deep dive.
Yeah.
Carbon emissions are not a philosophy, they are just another output stream in your process flow diagram.
Yeah.
You take the quantity of a resource consumed by a component like cubic meters of natural gas or kilowatts of electricity, and you multiply it by its specific emission factor.
And I find this framework incredibly empowering. Emissions aren't some vague moral failing that we have to feel guilty about. They are a rigid engineering metric, exactly like throughput or cycle time or defect rate. If you want to reduce your factory's carbon footprint, you don't need a PR campaign.
No, not at all.
You pull the exact same process levers we've been talking about. You increase flow efficiency, so heavy machines aren't idling for hours waiting for parts. You use dynamic scheduling to run your massive computing workloads in the middle of the night when the local power grid is utilizing cheaper, greener wind energy instead of daytime coal. You don't need to invent a brand new discipline to be sustainable. You just need to apply rigorous process engineering to the carbon stream.
It completely demystifies sustainability. It turns climate action from a political debate into an optimization problem. And engineers are exceptionally good at solving optimization problems when they're given the right metrics to target.
Okay, so we have covered a staggering amount of math today. We have Kingman's formula for variability, Little's law for queuing, matrix algebra for flow balances, and OEE for equipment effectiveness. Doing this math by hand for a single coffee shop is hard enough. Doing it for a massive chemical plant or a global software giant like Google is completely humanly impossible. Which brings us to the final piece of the puzzle. How is this discipline actually practiced today?
It is practiced in code. The entire discipline of process engineering has migrated away from whiteboards and spreadsheets and into programming languages like Python. Engineers use vast data libraries like pandas for statistical analysis and frameworks like SIMPy to build complex simulations.
This leads us to the concept of digital twins, which sounds like sci-fi but is very real. Explain what a discrete event simulation is and why building a digital twin is such a powerful tool for modern companies.
A discrete event simulation allows you to execute your static process flow diagram as a dynamic living computer program. You code the logic, and then virtual entities arrive based on statistical probabilities. They queue up, they seize virtual resources, they get processed, and they leave. A digital twin is when you build one of these massive simulations and you calibrate it perfectly by feeding it measured historical data from your actual real-world process.
So it basically lets you play God, but safely.
Precisely. Let's say you manage a live chemical refinery. You can't just casually test 17 different buffer tank configurations on the live plant floor just to see what happens. If you guess wrong, the plant might literally explode, or you might cause millions of dollars in unexpected downtime. But if you have a highly calibrated digital twin, you can run 10,000 different permutations of tank sizes in 5 minutes on a laptop, and the simulation will spit out the mathematically optimal setup without risking a single dollar or a single life.
But the source material flashes a massive neon warning sign here, the danger of bad data. You used a phrase earlier when we were talking about this that stuck with me, confident nonsense. Walk me through how a multi-million-dollar simulation becomes confident nonsense.
A simulation is ultimately just a mirror. It only reflects the assumptions you put into it. The danger is that modern software makes it very easy to build a massive, incredibly visually complex simulation.
Right.
But if you are too lazy to gather real data, and you just guess at the input distributions. For instance, if you assume your customer arrival rate is a smooth, clean bell curve, when in reality it is highly bursty and chaotic, your simulation will still run.
Right, the computer doesn't know you guessed.
Exactly. And it will output a result that looks incredibly precise. It will give you utilization prediction down to 4 decimal places on a beautiful color-coded graph, and it will be completely dangerously wrong.
Because the math is right, but the inputs were a fantasy. Confident nonsense.
Exactly. You must measure reality before you simulate. Measurement precedes simulation, always. If you simulate based on assumptions, you are just automating your own ignorance.
And that leads to what I think is the most exciting bleeding edge development in this entire field, process mining. Because we actually don't have to guess or assume anymore. Almost every process happening in the business world today leaves a digital footprint. Every time a customer service ticket is opened, every time a warehouse barcode is scanned by a forklift driver, every time a piece of code is committed, there is a digital event log created. It records a case ID, the specific activity, and an exact timestamp.
Process mining is revolutionary because it takes millions of those raw event logs, feeds them into specialized algorithms, and reconstructs the actual process as it truly exists.
Okay.
It doesn't show you the idealized, neat flowchart that the manager proudly drew on the whiteboard.
It shows the messy reality.
It shows you what is really happening on the ground. It finds the hidden, undocumented rework loops where things go backward. It exposes the shadow queues where work sits for weeks. It identifies the true bottlenecks that no one in management knew existed. In process mining, the behavior of the system itself becomes the data set.
It's like finally turning the lights on in a dark, messy room. You can finally see where all the furniture actually is instead of where you confidently thought you left it.
That's a great way to put it.
Okay, let's take a breath and bring this all together. What an incredible journey through the mechanics of reality. We started by looking at a busy restaurant kitchen, and we ended up algorithmically simulating digital twins in code. But the core truth, the golden thread connecting all of this, has remained constant. Whether you are refining crude oil in Texas, shipping cardboard boxes globally, or reviewing pull requests in a tech startup, the math is entirely the same.
The flow of discrete entities, the unyielding constraints of physical and human capacity, the devastating compound interest of hidden rework loops, and the undeniable nonlinear physics of queues. Throughput is always limited by the bottleneck, and delay always grows toward infinity as utilization approaches 100%. These are not trendy business theories pushed by consultants. They are mathematical laws.
Which brings me back to the promise I made you at the very beginning of this deep dive. You now possess the superpower to see the invisible structure of work. You know that capping WIP increases speed. You know that optimizing a non-bottleneck is a waste of time. You know how to read the matrix.
You really do.
But I want to leave you with one final, deeply provocative thought. I want you to turn this powerful analytical lens away from the factory floor, away from your company, and turn it directly onto yourself. Look at your own daily routine. Look at your own workload and how you manage your life.
Oh, this is a tough one.
It really is. If you were to map your own typical week as a process flow diagram, where is your structural rework? Where are you constantly redoing tasks or apologizing for mistakes because the quality was poor the first time you rushed through it?
And, ask yourself about the utilization trap, too.
Yes, exactly. Most importantly, deeply ask yourself this. Have you fallen into the utilization trap? Are you trying to maximize your own personal efficiency by booking yourself at 100% capacity? Do you schedule back-to-back meetings from 9 to 5 with no breaks, no time to think, and no buffer for emergencies?
Because if you do, the math guarantees you're failing.
Right. Because if you are living your life at 100% utilization, the math we learned today guarantees one unavoidable outcome. Your personal cycle time on everything you actually care about is going to grind to a painful, exhausting halt. You will feel incredibly busy, but you will get absolutely nothing of value finished.
You just become a human traffic jam.
A human traffic jam. You need slack in your system. It isn't laziness. It is a mathematical requirement for flow. Think about that the next time you look at your calendar and feel tempted to fill that one empty 30-minute block. Leave it empty. The math demands it.